Hello dear students, welcome you all. In this lecture I am going to discuss about the nuclear stability graph. Right? So in this lecture we are going to discuss about the stability of atomic nuclei. So many experiment has been done to find out the list of stable nuclei in the nature, and till now we have observed around 3,300 or more than that nuclei in the nature. Right? All these nuclei are basically isotopes of the different elements that exist in nature. So this list is increasing day by day as we are performing more experiments using more advanced techniques. Then the list of the nuclei is obviously increasing. So at present we have around 3,300 nuclei in the nature. Now out of those 3,300 nuclei, it is found that only 286 are stable, whereas the other are unstable. Right? Now, in these 286 stable nuclei, we have 252 nuclei which are non-radioactive. Whereas 34 nuclei are radioactive. Now, these are also included 34 nuclei in the list of stable nuclei. But they are radioactive. So, a question can be asked, if they are radioactive, then why we are calling them as stable nuclei? They are called stable nuclei because their half-life time is quite long. It is comparable to the age of the Earth, right? That's why they are included in the list of stable nuclei, right? In total we have 286 stable nuclei. Now if we observe or study all these 286 nuclei and we prepare a chart, then it is found that most of the nuclei in these 286 nuclei are basically even. Even means they have a even number of protons and a even number of neutrons, right? So this shows that these nuclei has extra stability as compared to the other nuclei in their neighborhood, right? Whereas odd nuclei, right, they are very rare. Only 8 odd nuclei has been found to be stable in the nature. Otherwise, other odd nuclei are not stable, they are highly unstable. So if I draw a table of all these nuclei, then you can see here. Right, so I can write it is for even, it is for odd, it is for even odd, and it is for odd even. Zn, Zn, even number of protons and even number of neutrons. here Z and N, Z and N, right? And here we have 252 and 34. So if we look at the 234, then it is 147 and it is 21. It is here total 8, I think it is 4, I will check it. Here we will have, I'm going to check it. So yes, I have written it here. 4 odd here in this category, 4 here, 53 and 4, 48 and 5. So total, I can say total number here, it is 286, it is 168, it is 8, it is 57, it is 53. So total these 34 are radioactive, whereas these are non-radioactive, right? So you can see from this table that the even nuclei, those nuclei for which the number of protons and number of neutrons both are even, they are maximum, right? They are total 168, whereas the odd, both proton as well as neutron odd, they are total 8 stable nuclei in the nature. Whereas if we look at the even or odd even, then we have nearly same 57, 53. So one thing is clear from this table, that nature prefer those nuclei for which number of neutrons and number of protons both are even. So although we will explain it in the nuclear models, but here I can say that this stability feature is arising because of the pairing of neutron and protons in their respective cells. When the protons and neutrons get paired, then there is extra stability. So that's why even means even number of proton means protons are paired, even number of neutrons means neutron are paired. So that's why they are having extra stability, whereas odd means extra neutron, extra proton, so they are obviously unstable, whereas even odd and odd even are mixed. So this is the feature that we observed when we did a careful study of all the naturally occurring nuclei, that is around 3300, right? And we found that only 286 nuclei are stable, right? Now we also got a very interesting feature from this table when we plotted a graph between the number of protons and number of neutrons in all these nuclei, right? So if I plot a graph between number of protons and number of neutrons, here it is number of neutrons n and here it is z. So when we plot a graph between this number of neutron and number of proton for all the nuclei that we observe in the nature, then it is found that this graph was having this type of feature. I'm drawing first of all a line here. This is the line that show n is equal to z, right? N is equal to z line, and but we observed actually that for the small a nuclei, I mean those nuclei for which z is less than 20, right? For all those nuclei, z is equal to n, means the graph is a straight line. If I took 20 here at this point, 20, then up to this point the graph is a straight line. But as the z increases, right, now it is becoming higher and higher, more than greater than 20, then it is found that the number of neutron start becoming more than number of protons, right, and the graph start deviating in this way, you can say, right. So this type of deviation is observed when we plot a graph between number of neutron and number of protons for all the nuclei. I am showing you the actual graph that has been observed. You can see from here what I was saying. This is this line, right? This line is the line that is n is equal to z. It is written here, right? But you can see this line is only valid up to this point when z is equal to 20. It is written. The line of stability follow n is equal to z for z less than 16, or we can take z less than 20. I told you, but this is the actual situation. You can see here. Now, as we go toward this side, as the number of proton increase, I mean we are going to the heavier side, heavier nuclei side, then this graph tends to deviate from the straight line and it start deviating toward this side. It means the number of neutrons are now increasing. You can say here stable nuclei are represented by these bluish dots here, right? Whereas stable nuclei cluster very close to the line of stability. You can see here, this is the line of stability, right, that is observed. All the nuclei that fall on this line are highly stable, right, whereas the nuclei that are very close to this line in the form of small clusters, they are also stable, right, but those nuclei which fall on the line, they are highly stable, right, whereas the nuclei that are unstable, that are in the bands along the both side of the line of stability, you can see with these bands, right, they are represented by this color, you can see here. These are the bands of unstable nuclei on both the side of line of stability, right. As z increases, then you can see this is bismuth, z is equal to 83. This is the last stable nuclei, and if we go beyond this point, then the nuclei are no more stable and they undergo radioactive decay, and they want to come back toward this side, undergoing either alpha beta or alpha beta. In beta we can say it is beta positive or beta negative decay or electron capture, right. So this 83 bismuth 209 is the last stable nuclei that exist on this line. If we go beyond that, then all the nuclei are unstable and they undergo radioactivity, right. Now all those nuclei which are either on this side, right, or either on this side, now they also have the tendency to come toward this side, toward the line of stability. So what they can do? Now they can, I told you, they can undergo alpha or beta decay. Now alpha decay means emission of alpha particle, 2He4 helium atom nucleus, combination of 2 proton and 2 neutron. We will discuss alpha, beta and gamma decay in detail in the chapter of radioactivity. Whereas the beta decay means emission of either electron or a positron, or it is electron capture. We will also discuss it in detail. So, but at this point of time, you only remember that either alpha decay or beta decay can take place. So, by undergoing alpha beta decay, the nuclei on either this side or here, they can come toward the stability zone. If the nuclei is on this side you can see, then it can come toward this side by undergoing a beta positive decay, right? But if the nuclei is on this side, then it can come toward this side, then it can undergo a beta negative decay. Similarly, if the nuclei is present here, then it want to come toward this side, then it will undergo alpha decay, right? So you can see that all the nuclei that are not on the line of stability or nearby to the line of stability, they have the tendency to undergo alpha, beta and gamma decay, we can say, but alpha and beta decay are dominant because they leads to the reduction in either neutron number or proton number or both, right? We will discuss it in detail when we will discuss the chapter of radioactivity. I will recall this graph there also. Now, I want to explain why this feature is observed, why the number of neutrons are higher than number of protons in heavy nuclei, in all those nuclei for which Z is greater than 16. Why it is there? So, to understand this graph, we have to recall that what type of forces are operating inside the nucleus, right? This is nucleus. And we have protons positively charged. These are protons, but we also have neutrons inside the nucleus as per the proton-neutron theory. Now, these protons and neutrons are wounded together inside the nucleus by strong nuclear force, which is attractive in nature, right? These are bonded together by strong nuclear force, right? Now, the another force that exists inside the nucleus, that is electrostatic repulsive force between protons. We know very well that strong nuclear forces are charge independent. I mean, they can exist between proton-proton, between proton-neutron, between neutron-neutron. They have nothing to do with the charge. Whereas the electrostatic forces are charge dependent. So obviously, when the protons are there inside the nucleus, they are going to repel each other, and if the strong nuclear force is not there, the nucleus won't be formed, it will disintegrate, but the strong nuclear force is binding these neutrons and protons together inside the nucleus. Now, when the nucleus is formed, initially for Z less than 16, the number of neutrons is equal to number of protons, because the size of the nucleus is small, and the strong forces that has a range of the order of 10 raised to power minus 15 meter, they are now capable of handling the repulsive forces. I mean, the strong forces are dominant, I can say. But as the number of protons increase, I mean Z increase, then the size of the nucleus also increase. Now, when the size of the nucleus increase, the electrostatic repulsive forces between the protons also increase. Now, the stability of the nucleus decrease. So, in order to adjust this, rising repulsive force, the number of neutron increases, right? Due to the increase in the number of neutron, there is nothing change in the electrostatic repulsive forces, but the attractive forces, strong forces, they also increase, right? So that's why when we are going toward the heavy nuclei, you can take the example of 92 uranium 238. You can see here the difference between number of neutron and number of protons, right? They are not equal because number of neutron is very high as compared to the number of protons, and these extra number of neutrons are going to counter the repulsive forces between the protons, and that's why the nucleus will be stable. So this is the reason why the nuclei for Z greater than 16 has large number of neutrons. I mean neutrons more than number of protons. But as far as Z less than 16 or 20 is concerned, now nuclear forces are enough strong to handle the repulsive forces. So they are equal and we have a straight line, right? So this is about this graph. This is very important graph that tell us about the alpha decay, beta decay, and possibility of electron capture and all these radioactive processes in the nature. When we will discuss the radioactivity chapter, in that I will again recall this graph and we will explain why this beta decay, alpha decay takes place and how they increase the stability, right? So this is about the nuclear stability graph that we have discussed here. So thank you very much.